Assalamualaikum, I am Nurin from Group F. In this video, we would like to present our assignment, which is laminar flow. Firstly, we start our presentation with introduction of laminar flow. Laminar flow is characterized by the smooth and orderly movement of fluid particles along parallel layers or streamlines with little or no mixings between adjacent layers. In fluid mechanics, one of the mostly widely studied cases of laminar flow involves the flow of fluid over a flat plate. This type of flow finds application in various fields, including the study of plate heat exchangers, aerodynamic, surface in the vehicle, surface coating process, and microfluidics. When fluid flow over a flat plate, the fluid adjacent to the surface is affected by the interaction between the fluid particles and the surface. This creates a region of distributed flow called the boundary layer, where the effect of viscous forces is felt. This boundary layer is essentially a thin layer of fluid adjacent to the surface, characterized by a rapid change in fluid properties as it moves away from the surface. From the leading edges of the plate, the thickness of the boundary layer increases until it reaches a specific point called the entrance length. At this point, the boundary layer stops growing and a fully developed flow starts to form. This is the theory of laminar flow. A sphere in stop flow at very low Reynolds number, an object moving through a fluid experiences a drag force in the direction opposite to its motion. The Reynolds number is the ratio of the initial force to the shearing force of the fluid, how fast the fluid is moving relative to how viscous it is, irrespective of the scale of the fluid system. What is Reynolds number? Reynolds number is a dimensionless quantity that is used to determine the type of flow pattern as laminar or turbulent while flowing through a pipe. Reynolds number is defined by the ratio of initial forces to that of viscous forces. As the Reynolds number increases, such as by increasing the flow rate of the fluid, the flow will transition from laminar to turbulent flow at a specific range. The Reynolds number is named after the British physicist Osborne Reynolds. He discovered this while observing different fluid flow characteristics like flow of liquid through a pipe and motion of an airplane wing through the air. And this is the equation of Reynolds number. Re equals to rho Vd over mu. V is for velocity, d is for diameter, and mu is for viscosity. But for kinematic viscosity formula is Vd over V.
The objective of this project is to find the velocity at the flat plate by using CFD simulation. Second, to find the effect of airflow on boundary layer thickness and to learn how to use and set up CFD simulation. Geometry, detail and dimension. The dimension for flat plate is 1 meter for vertical and 0.5 meter for horizontal.
Hi, so now I'm going to show you the simulation of our fluid flowing. So now I'm going to start by sketching a geometry. So here's the geometry. Given our geometry, our dimensions are by 1 meter and by 0.5 meter. So that's what I'm gonna sketch a plate now. It's considered as like a boundary plate. So we choose XY plane as our starter, and then we sketch a rectangle of the graph, and then we're gonna set our dimensions over here. For horizontal is gonna be 0.5 and for vertical is gonna be 1, which is 1 meter of course. And now we're going to change the rectangle to a plate, to a solid plate. As you can see, there's a solid plate over there. And before that, we have to save our file just to make sure that the file is still there, so it's not lost during our process. And now we can exit the file and proceed with our meshing process. So first of all, I'm going to mesh this whole plate over here. and as you can see the line is crooked, one up one down, so that's not we want. So we're gonna make it straight. So I'm gonna start by face meshing. I'm gonna face mesh over here, and then I'm gonna generate. And then as you can see the line is almost straight, but that's not we want, as we want to see clearly the movement of the boundary. So I'm gonna start meshing over the top and bottom of the plate, which is two edges, and I'm gonna change the number of divisions to 50, and just to make sure I'm gonna change the boundary line to hard. Then as you can see there's a rectangle type of shape of all over the plate, and then I'm gonna change the meshing side over the left side of the plate, which is our inlet of course, and I'm gonna put some bias over there. Since it's our inlet, our airflow is gonna flow through that, so I'm gonna set the bias factor at 70, and as you can see the meshing is like the meshing shape is such, and this is not enough as well since there's an outlet left in the boundary plate. So I'm gonna do the same, exactly the same as I did on the left side of the plate, just that I'm gonna change the reverse pattern of it, because you can see this reverse pattern over the left side of the plate. So I'm gonna reverse it, set to I'm gonna reverse it and apply for that line, and then as you can see it has the same division line as the left side of the plate. So I'm gonna generate, and then you can get the the whole meshing of the plate. So now I'm gonna name each section of the plate. So I'm starting with the face, which is airflow, since the airflow is gonna cross the boundary plate. And then the left side of the plate, I'm gonna name it as our inlet, and the right side of course is gonna be outlet, and the bottom is gonna be plate. And for the top, we usually ignore that side since the pressure will not be affecting over there, so I'm gonna just put this as far side pressure, just to know that it's not affected at all. And then we can save this file, and then we can go back to the original file and update the work over there, and then we can carry on to our setup to set up our plate. As you can see, this is the symmetry line of our plate. There's a gap over there. This is an actual symmetry line of our plate. So now what I'm going to do is do some changes, change some settings and set some airflow values over here. So first of all, I'm going to change it to laminar, the flow, and then I'm going to change the properties of air, which is the value. The density I'm going to change to 1, and the viscosity I'm going to change to 0.0001. And then make sure the boundary conditions is set correctly. I'm going to change the airflow to 2 meter per second. And then the far side pressure, I'm gonna set it as symmetry, which is the usually ignored side. And then the method is simple. There's a term simple over the method, so I'm gonna choose that. And then for the residual, I'm gonna, since the number of iterations is 1000, so I'm gonna go for higher accuracy, which is 0.000001, which is 6 digits in total. And then I'm gonna initialize this whole setup. And once I've set the speed, I'm gonna initialize it, and then I'm gonna run calculation. I'm gonna run the irritation graph by running the calculation over the plate. Make sure make sure the number of irritations is 1000, so I get the accuracy reading. As you can see, the graph is still converging. So in order to get a stable reading, so I set the number of irritations to 1000. As you can see, the graph is stable for now. And once the calculation is completed, I'm gonna save this graph, irritation graph, and then I'm gonna go to my result option. So this is our final result going to be, and I'm going to set a contour vision. As you can see, this is a vision for contour vision for velocity, for pressure, and this is the contour vision for velocity. And before I move on to chart, I'm going to set a line to plot where is my reading going to take according to our dimension given. And for now, I've moved to chart, and then I'm going to name it as airflow, the chart name, and I set the x-axis and y-axis. And then for the reference, I took the line 1 just now, the line I took. So here's the graph. As you can see, there's a sharp thing over there, so I'm gonna make it a bit curved. Just I've increased the line to 250. I've increased the sample to 250, so you can see a bit curve at the line over there on the graph. So this is our graph for 2.0 meter per second airflow. So I'm gonna save this graph as well, and then I'm gonna compare to our second plate of graph. Yeah, and this is our symmetry for second plate, the same dimension as well. Nothing has changed except for the airflow, which is 2.5. Everything is exactly the same as the previous plate. It's the laminar, the air changed, the density changed to 1, and then the viscosity changed to 0.0001. Here are the boundary conditions. Yeah, for the inlet, I'm going to change the airflow to 2 meter per second, 2.5 meter per second, as you can see in the video. .5 meter per second. Okay, and then I'm gonna set the far side pressure as symmetry, usually the ignore side. And then I'm gonna go to methods, change it to simple, and then I'm gonna go to residuals. As before, I'm gonna change the irritation to more accuracy, so I'm gonna go to 0.00001, make it lower so I get closer readings. And then I'm going to initialize it, copy it from inlet, and then the rest is nothing. I'm going to initialize it, and then I'm going to run calculation. Going to change the number of irritations to 1000 as before. Then as you can see, our graph is started converging, and then converge again as well. And then for a few seconds it has been stable. The graph is stable for now until the end of the line. So I'm gonna save this graph as well, and then I'm gonna go to result to compare both of the plate of the graph. So this is our final results. This is how it's gonna be. So we'll go to contour as well as usual. Just change to, this is our contour vision for pressure. Change it to symmetry too. This is our contour vision for pressure. Here it is. And then this is the contour vision for our velocity. And then before that, as usual, I'm going to set a line plot in the middle of the plane according to our dimension given. 0.25, change it to 0.25 as well, and then I set here as 1, and then the sample I'm gonna set as 100. So as you can see, the line is plotted in the middle of the plate. And then I'm gonna go to chart over here, and then as usual I'm gonna do the exact same thing as I did before. Change the chart to airflow for the title, and then x-axis change it to velocity, and y-axis I'm gonna just set it as y. And then for the location I'm gonna set as line 1, apply. As you can see, this the same line I get over here for 2.5 meter per second of airflow. And then since there's a sharp line over here, I'm going to change the sample to 250 like before. And then there's a little bit converge over there, or curve over there. So now I'm going to compare both of the graph on this chart over here. Just going to add over here and then take from the previous file, fluid, take the previous slide, line 2, yeah, here it is. So this is the difference between our both graphs. This graph shows that different value of airflow have different type of boundary layer of thickness. So we can conclude that boundary layer of thickness is affected by the velocity or airflow of a certain laminar flow.
From the simulation results, we can understand that higher velocity airflows has different effects on boundary layer thickness, and the flow, laminar or turbulent, can be determined by the Reynolds number found. In our simulation, 2 meter per second airflow has a Reynolds number of 1.936 times 10 to the power 5. Most of the plate is covered by laminar flow, which is less than 5 times 10 to the power 95. This aligns with the theory that has been stated previously. As we can see in the first picture, the shade of orange is lighter, which shows that boundary layer thickness is thinner. For simulation of 2.5 meter per second airflow, the Reynolds number is 2.442 times 10 to the power 5. The slightly higher velocity results in thicker boundary layer, but it still remains within the region of laminar flow. From the formula below, we can understand that Reynolds number is directly proportional to velocity. Evaluating velocities of airflow on boundary layer thickness. First, let's look at velocity profile for 2 meter per second. The velocity profile in laminar flow is relatively smooth and gradual. Velocity near the wall increases gradually from 0 to free stream velocity, forming a stable laminar boundary layer. For 2.5 meter per second, the velocity profile remains laminar, but it might be more stretched compared to 2 meter per second. The higher velocity can result in more rapid increase in velocity near the wall due to its increased momentum. Thickness, on the other hand, for 2 meter per second, the laminar boundary layer thickness is relatively smaller than 2 meter per second. The orderly movement of fluid particles near the wall results in thinner boundary layer. The Reynolds number of 1.963 to the power of 5 is within the laminar range, and the flow remains stable without significant disturbance. For 2.5 meter per second, despite the laminar flow, the boundary layer thickness is expected to be slightly larger. The higher velocity increases the momentum of the fluid, leading to a thicker boundary layer compared to 2 meter per second. This phenomenon can be explained in a simple form. For velocity profile, the laminar flow pattern is maintained in both cases due to its relatively low Reynolds number. Laminar flow occurs in the Reynolds number is below a critical value. In this case, both Reynolds number fall within the laminar range. The velocity profile is influenced by the smooth movement of fluid particles in laminar flow. The increase in velocity is more gradual in laminar flow compared to turbulent flow. For thickness, on the other hand, the increase in velocity generally leads to thicker laminar boundary layer. This is because higher velocities results in increased momentum and shear at the wall, leading to thicker layer of fluid near the surface. However, it's important to note that boundary layer thickness in laminar flow is generally smaller compared to turbulent flow at similar velocity.